Well, hello there, this is Joe Van Cleve, and welcome to part 2 of the Abacus. Today, in this second part of this new series, I'm going to talk a little bit about the early history of the abacus and the Greek and Roman and European counting board. Stay tuned. When many people think of the abacus, you think of the little bead frame calculators, either Asian origin, Japanese and Chinese, or the little colored bead frame devices that are found in toy stores for kids. But the abacus actually predates the bead frame idea, and we go back at least as far as the Greek culture, where they had what was called the counting board. There is one archaeological example called the Salamis tablet, and the Romans inherited the counting board from the Greeks, and what the Romans did with it is two different things. Number one, after the fall of the Roman Empire, European culture inherited the counting board, and it was used throughout Europe up until as late as the 17th or 18th century. But the other side of that evolution was that Romans also took the counting board from the Greeks, and they developed a tablet with grooves in it and clay balls that had a 1-4 configuration. And they traded along the Silk Road with the Chinese Empire. And the Chinese got the 1-4 bead abacus idea from the Romans, and because bamboo is so plentiful in Asia, they eventually developed their bead frame calculator that we are aware of. But what I'd like to cover today is a little bit about the counting board and how it works. What I have here is a graphical representation of the Salamis tablet or counting board of the ancient Greeks or Romans, just made of foam core board, but I'm using regular decimal notations of place value system instead of the Roman or Greek system, just to make it easier for us to understand. But the Salamis tablet was divided in half along this vertical line. This half is for negative values and this half is for positive values. And then you have rows that are graduated by place value, 1, 10s, hundreds, thousands, and you have pebbles or counters to keep track of the numbers, and I'm using just these metal nuts. The spaces between the major place values count for 5. So this is 5s, this is 50s, this is 500s, and this is 5,000s. So I'm going to do a little math problem here, and I'm going to add 135 plus 248. So the way we enter numbers, there's 100, 30, 3 10s, and a 5. So our first number is entered on the board, and we're going to slide those over to get them out of the way of the middle. And our next number is 248. So we're going to put 200. Now the 40, we're going to do a 50 and a minus 10. And the 8, we're going to do a 10 and minus 2. Then what we're going to do is we're going to have to justify the results or simplify it into the answer, and we do that from the bottom up. So we have -2 here and we have +5 there. That's 3. These two cancel each other. They're negative and positive. And the answer forms itself as 383. There's 3 in the hundreds. There's a 50 and 3 10s, that's 80 and 3, so 383. So next, we're going to take our answer of 383, and we're going to add 479 to it. So again, we're going to enter the 400, which is 500 and a minus 100. 70 is 50 and 20, and 9 is going to be a 10 and a -1. And now we have to justify or simplify it, and we go from the bottom up. So these two ones, negative and positive, cancel. 5 of these 10s can be promoted to a 50. 2 of the 50s can be promoted to 100. And these 200s cancel, negative and positive. And the answer is 800, so 500 and 3 100s, 862. Okay, we're going to take our 800 62, and we're going to subtract 686 from it. Now these numbers are not anything special. These problems I just randomly chose. But so first thing is we're going to enter 686 on the board. So 500 and 100 is 600. 80 is 100 and a minus 20. And the 6, of course, is a 5 and a 1. Now, because we're going to subtract, we're going to turn this number into a negative number, and we're going to do it by simply moving the counters to the opposite side of the line. Now that is a negative 686, and now we're going to combine them together to get the answer. So we start at the bottom place value, the units place value, so these two ones cancel. Here we have a minus 5 and a plus 10 cancels into a plus 5. Two tens of 5, these two hundreds on each side cancel, and these two 500s cancel. And our answer is 176. Well, in actual historical fact, the Salamis tablet was a little more complicated than that, because the Romans were using not only base 10, but they were using base 12 for some of their calculations. And they didn't have the place values based on tens. They had their Roman numeral place values, but they were doing math with Roman numerals. But in the medieval Europe, they inherited the counting board, and many noblemen, kings, and later on banking houses all used a version of the counting board to keep track of financial calculations. And what they used instead of pebbles or zinc hardware nuts is they had coins cast, and they were imprinted on one side with the insignia of the nobleman, the king, or the banking house, and on the reverse side it was blank. Now, years ago, I took a trip up to Colorado Springs, Colorado, and visited the Numismatic Museum. There's a coin or numismatic museum up there. And they had a number of examples of coins that were only minted on one side, and they were blank on the reverse side. And I only realized later on, after I started studying the history of the abacus and the counting board, I realized that those were most likely counting tokens, which in French was jetons. They were used for counting. The counting boards in Greece and Rome were often carved of stone. They were probably also made of wood, but we don't have any surviving record of those. In Europe, they were often made of wood, like tables with the lines set in them. But tax collectors and other traveling kinds of people that had to use calculations often had a portable version. It was a cloth that they carried with them that had the lines stitched or woven into them, and they could carry their counting casting stones or counters with them, and they would go from village to village and town to town and settle the accounts of people using that particular method. It's also evident from the legacy of the counting board, the idea that you have these intermediate 5 values, 5 ones and 5s, and 10s and 50s, and 100s and 500s. It's kind of easy to see how you go from that to the abacus having 5s and 1s. The upper row, the heaven row, being worth 5 each bead, and the bottom row, each bead being worth 1. So there's a direct connection with that. In part 1 of this series, I told you that this part 2 would be about my history of making abacuses, but I felt it necessary to first get into a little bit of the history of the abacus from its earliest days and how it evolved, because understanding how it works is important to understand how the evolution of the device occurred. So we go from counting boards using counters or stones to a bead frame calculator with, in China, 2 and 5s on each row. And then as the monetary system and the numerical systems began to change into more of the way that we understand in the West to be a base 10 decimal system, with each row, each rod being powers of 10, it's easy to see how it becomes more like our modern numerical system. Now, I've looked at a number of videos about Chinese merchants using the Chinese 2-5 abacus. And I've noticed in a lot of these videos that rarely, if ever, do they actually use the upper 5 bead or the bottom 1 bead. They're all using just the 5 beads in the middle, the 1 5 bead and the 4 bottom ones, just like a Japanese 1/4 soroban. The most efficient method of abacus, the most efficient design, turns out to be the 1/4 design that the modern Japanese have used since the early 20th century. Even though many cultures still use the 2/5, they're really using it as a 1/4 device. And I think that's pretty important to point out. And so that gets us to the subject of the 1/4 abacus and how it works. The most challenging part of an adult trying to learn the abacus, the modern 1/4 soroban abacus for the first time, is grasping this idea of complementary numbers. Understanding complementary numbers is the key to understanding how the modern abacus works. So let me show you how that works. As I explained in the last episode, the abacus is cleared by moving all the beads away from the bar so that the bar is cleared. And you can choose a place value. We'll just choose this one as the ones or the units column. And to enter numbers, you move them up toward the bar or move a 5 bead down toward the bar. So that would be 2, for instance, 3, 4, 5, 6, 7, 8, 9. So you can represent a number from 0 to 9 on each rod. So simple addition problems like, for instance, 1 plus 3 is 4, or 5 plus 2 is 7. Those are easy to see. What's not so evident to understand is, for instance, a problem like 2 plus 4. This is where we get into the idea of complementary numbers. So let me show you how that works. Let's enter our number 2. Okay, this is the 2 value. It's been entered. Now we want to enter a 4, but we don't have 4 beads left to enter. And so instead of entering 4, we're going to take the complement of 4 with respect to 5, which is 1, and we're going to do the opposite operation on it. So instead of adding 4, we're going to subtract the complement, which is 1, and then we're going to add the 5 to say we did a 5's complement. So in our mind, you're not supposed to think 4 is 5 minus 1. What you're supposed to think is, I don't have enough beads to do the operation directly, so instead of adding 4, I subtract the complement and then move the 5 to say I did a 5's complement operation. And in the process of doing that rule, the number 6 forms itself automatically on the abacus. Okay, so let's try another problem like 3 plus 4. So here's 3. And again, we want to enter the 4. We don't have a 4 beads to move up. We're going to subtract the 5's complement and then say we did a 5's complement operation. And all of a sudden, the answer 7 forms itself on the abacus. Okay, that is the essence of 5's complement arithmetic, and that's how you can add simple numbers together using that rule. Also, subtraction works the same way in reverse. Okay, there is also another thing called the tens complement. So, for instance, let's say 3 plus 8. 3, there's 3. Now we want to add 8 beads to that. Well, we only have a value of 6 left, this bead and that bead. We can't add 8. So the tens complement of 8 is 2, and I'm going to do the opposite operation to the complement. I'm going to subtract the complement, and then I'm going to put a 10 up there saying I did a complementary operation. And all of a sudden the answer 11 forms itself, a 10 and a 1. Okay, that's tens complements operations. We could do a similar problem. So for instance, 4 and 7, for instance. So there's the 4. Now we want to add 7. We don't have 7 left, so we're going to subtract the tens complement of 7 and put up the 10. All of a sudden the answer 11 forms itself on the abacus. We don't actually think of plus 7 being 10 minus 3. We just have to know the complementary numbers, the 5's complements and the 10's complements. When I was a young man in high school and I first discovered the abacus, One of the first resources I went to, and keep in mind this is in the early 1970s and there was no internet. You had public libraries, but they hardly had anything about this kind of subject. So it was really hard finding these kind of resources. But I found two books. And this is probably the most famous book in the Western world on the Japanese soroban by Takashi Kojima. Anytime you see somebody talking about, I have Kojima's book or books, this is what he's talking about. The Japanese abacus, its use in theory, this is essential for understanding operating the soroban. And the subsequent follow-on book, Advanced Abacus, Theory and Practice. If you're interested at all, get these books, okay? But the thing that I soon discovered as I went through the problems in the book, there's a lot of numerical problems that you can work. Like in the back of the book, there's whole columns of numbers you can practice adding and subtracting, even multiplication and division. But the thing about addition and subtraction that frustrated me for a long time is there's certain problems where you're not just using 5's complements and not just using 10's complements, but to do the one problem, you have to do both a 5's complement and a 10's complement in the same problem. Let me show you an example. The problem is 6 plus 7. So we're going to enter 6 on the soroban, 5 and a 1. Okay, now we're going to add 7. So we don't have 7 beads available on this units rod. So we're going to have to add a 10 and subtract the 3. Okay, so we can add the 10 now, and we have to subtract the 3. But we don't have 3 directly to subtract. So we have to do a 5's complement of subtracting the 5 and adding back the 2. And the answer of 6 plus 7 becomes 13, of course. So you have this problem nested within another problem. The way I finally learned this through a Taiwanese abacus teacher who lives here in New Mexico. And she taught me that the way you think of this problem is you enter the 6, and now when you want to enter the 7, you have to think of pushing up 7. In other words, 7 in the abacus is a 5 and 2 1s. So you take a 5 and the 2 1 and you push them all both up at the same time, and then you do your 10's complement bead. So, and it forms itself as 13. Let's look at that again. 6, I can't do it directly. I need to do a complementary operation. You push 7. You're pushing a 2 and a 5 up, and then you do your 10. And that's the way you can do the nested complements problems that have both a 5 and a 10's complement in them. Once I understood this principle, it made the abacus so much easier to use. Years ago, as I was studying Kojima's books and had a few abacuses in my collection, and I was trying to understand an easier way to operate these nested complement problems and to be able to gain up speed in my calculating skill, so I could go and add up columns of numbers faster than before. In the process of doing that, I kind of came on this roadblock of not being able to figure out easily how to do the nested complementary problems. And so in my usual way of doing things, I figured I could just redesign the abacus and make it a little bit easier to understand. And so what I did was I went back, and I didn't really know much about alternative types of abacuses like the Russian abacus that I showed you earlier. I didn't know about the Russian abacus at the time, but I figured that you could make an abacus with 10 beads, and it would be simple to use because each row having 10 beads means you can do 10's complement problems, and you wouldn't have to worry about the nested 5 10's kinds of problems. There's no 5 bead thing going on. And then I decided, well, just the same way that the Japanese took their 1-5 soroban, and they eliminated one of the unit beads and made it a 1-4 abacus where you can represent 0 to 9. In the same way that they did that, why don't I take one of the beads away from the 10 bead abacus and make it into a 9 bead abacus? And so I was thinking about this kind of stuff back in the late 1980s, okay? And I was thinking, okay, I'm going to modernize the 10-bead abacus and I'm going to create the 9-bead abacus. Let me show you what I came up with. So this is the late 1980s, and I could not find genuine abacus beads anywhere in my town, and you really still can't actually. So the only thing I could find were these little craft beads, these faceted craft beads, and I didn't want to use bamboo rods because the holes in these beads are too small. So I ended up going to the craft store and I found these wires that are kind of have this green paint on them. And these are floral wires for doing floral arrangements. But it turns out that these beads slide really easy on the floral rods, but they don't slide too easy. In other words, you could hit them real hard and they won't bounce. There's a little bit of friction there where they end up staying where you put them. So I built this really primitive frame, not very sophisticated woodworking at all. This is the actual first 9-bead abacus that I made. I can't remember, 4, 8, 12, 15 rods. And the way this abacus works, of course, is there's 9 beads on each row, and you clear the abacus by moving the beads down like that. Because you don't have the dividing bar and you don't have the 5 beads up on top, clearing this abacus is a lot quicker than having to go like that and then running your finger along the top the way you do with the other kind, with the soroban. I was also working on the idea of how can you make it quicker to operate. The problem with having 9 beads is when you want to move a number like 4, 5, or 6, or 7, you have to be able to quickly be able to discern the size of the group. You know, is that 4 or 5? And you don't want to stop and count them because that just is tedious and slow. You want to be quick at this. And so I experimented with several different color schemes, and I came up with this alternating dark and light color scheme. I had experimented with several different ideas. One of them was to make them all one color except for the middle bead. Because having 9 beads, there's an odd number of beads and you'd have a middle one. And it was okay. You could discern 4s and 5s pretty easily, but when you start getting up into 6s and 7s, it's kind of odd because the position of the black bead changes in that group depending on where you are, whether you're grabbing it from this end or somewhere in the middle. So it wasn't consistent and it was kind of confusing. So then the other idea I had was to alternate them and make them in groups of 3s, 3 light, 3 dark, 3 light. And where you can easily grasp groups of 3s visually, it was harder to use again because it depends on where you're at. Like here, a group of 5 is 3 and 2, but in the middle, a group of 5 is like that. It doesn't look the same. So there was a lack of consistency. And that's where I came up with this idea of alternating the colors, because what I discovered with it was an even number of beads, like here's 4, an even number of beads always has the opposite colors on the ends, right? Maybe I should do it down here easier. So a 4 has a black and a white bead on the ends, whereas an odd number like 5, the end colors are always the same, or 7, they're always the same. Whereas 6 is even, it has opposite end colors. And so there was a consistency about that worked regardless of where in the group you grab the beads. Like here's a group of 6 from the middle, and it has the same rule. It's even, and it has opposite colors. So that's why I went with this opposite colored, alternating colored design idea for the abacus. Now, what's interesting about this particular abacus, what's interesting to me about it from a personal standpoint is at the time that I made this, I was working as a technician at a TV repair shop. So back in the late 80s, I was a service technician in the video consumer electronics business. And I would not only do home service calls, but I did most of my repairs in the shop on a bench. And part of my job was to total up receipts and estimates of repairs for customers. And you would have to have the labor and the parts and the tax and all that. And so instead of using a calculator, an electronic calculator, I started getting interested in the idea of, well, I was already interested in the abacus. I had already made my first 9-bead abacus, and I decided, you know, just like in Asia, where those people in those markets and shops, they use their abacuses daily, it's part of their life, why can't I, in this day and age of the computer in modern America, why can't I take my 9-bead abacus and start using it at work? Now, obviously, the biggest problem with this, it's not the customers, because the customers don't know what you're doing in the shop. They're not back there at your bench. The biggest problem, of course, was my boss. I had to convince him that I was accurate with the abacus and I wasn't making any mistakes. And so I initially, one day, just brought the abacus in and started using it. And he kind of would check my totals before he called the estimate in to the customer, but he soon discovered that I was accurate and I wasn't making any mistakes. So this abacus was actually used in the United States of America in a retail business for calculations. And so there's a little interesting story about it. It's not very well made. It's pretty primitive, and it lacks all kinds of craftsmanship, but it means a lot to me for that reason, because I actually used it, and it was my very first 9-bead abacus. So do you remember that earlier problem that I showed you that I had problems with, the nested complements problems of 6 plus 7? Let's see how that works on the 9-bead abacus, shall we? There's 6. So to add 7, you subtract the 10's complement and add the 10. There's 13. Easy peasy. You might also be interested in the idea that where did that 10-bead colored bead frame toy thing that you see at toy stores, where did that come from? Well, it turns out that when Napoleon invaded Russia, he and his men discovered the Russian 10-bead abacus. They brought it back to France, where eventually it became a child's educational abacus, and we inherited that in America from the French in our culture, and that became the 10-bead kids toy abacus. So that came to us via Napoleon from the Russians, in case you're interested in that little bit of history. So anyway, this was part 2 of the Abacus series. I hope you found some interest in it, and I hope this piques your interest enough to maybe take a piece of paper, draw some lines on it, and get a handful of coins, and maybe start playing around with the idea of the counting board, and maybe find yourself an abacus or a soroban. Until next time, this is Joe Van Cleve. Have yourselves a great day.